Hello students, very good morning to all of you. This is Chandrasekhar, Physics faculty, Tungal College. Welcome to Tungal online classes. Today we have to discuss about the capacitor filter advantages and disadvantages, and next the second filter is series inductor filter, and third one is the L section filter, and fourth one is the pi section filter. We have to discuss one by one in this manner. Okay, so already the capacitor filter has explained in the previous class. So as the capacitor XC is equal to 1 by omega C, that is 1 by 2 pi FC, it offers the reactance. Reactance means what, Nana? Which opposes the flow of AC. So what happened here? Whenever the frequency is there, whenever the capacitance is large, then what happened here? So that means XC is equal to 1 by 2 pi FC. Whenever the value of C is very large and also frequency is very large, then XC becomes decreases. XC decreases means what? It offers low reactance path. That's why what happened? This is the capacitor. Through the capacitor AC component, it is allowing through it, and it is going to get grounded, and AC component within the rectified output can be filtered in this manner. Only the DC component only it is flowing through the load resistance RL when we are applying both AC plus DC from the rectifier output. It was already given. So in the previous class it was completed, and also waveforms also it was given. So for the positive half cycle, for the first positive quarter cycle, it is going to get charged. So this is the output of rectifier. This is the filtered output. Understanding? So whenever the rectified output it is going to get increasing from 0 to maxima, then capacitor it is going to get charging. At the point P it was fully charged, right? For the second quarter cycle, what happened here? It is decreasing from maximum to 0. So whenever it is maximum to 0, then what happened? The capacitor discharging slowly due to the RC time constant, right? If the RC time constant is very large, then what happened? It is very slowly it is going to decrease slowly like that here up to PQ. So whenever it reaches Q, then what happened here? The third quarter cycle, during third quarter cycle from 0 to maxima it is rising. So whenever it rises, and again the capacitance charging, recharge in this manner Q to R, and again whenever the pulsating DC decreases from maximum value to 0, again from R to S it is decreasing slowly due to the RC time constant. So here in this manner, this one is the output waveform from the capacitor filter circuit, right? So this is only you have to explain in brief, right, Nana? So next coming to that here, what it is? Advantages. What advantages it has? Only single capacitor, that's why very low cost. Okay, maybe 1 rupee, otherwise 2 rupees, otherwise below 10 rupees, that is the cost of this one. Okay, very easily we can able to prepare, and it one is the simplest circuit, smallest circuit, it occupying less space, and it was rugged. Okay, and small in size and less in weight, and suitable for both half wave rectifier as well as full wave rectifier. Understanding? And next coming to that disadvantages, what the disadvantages are there means, it is low ripples at heavy loads. As the load increases then ripples are there here. That means that ripple factor that is depending upon the load, right? Next, it depends on load resistance RL. What is the meaning of that? It depends upon load resistance RL. So with the variation of load resistance, the ripple factor that is at output becomes changes, right? And next one is The capacitor draws more current. The capacitor draws more current means what? So as the circuit, in the circuit capacitor is there na, here it is drawing more current. That is the disadvantage with this one. So this is about the capacitor filter. So now the next one is we have to discuss about that one is series inductor filter. The next one is, so that one is called as, the first one it is called as capacitor filter, otherwise you may call parallel capacitor filter. And the next one is series inductor filter. Why the capacitor in parallel? See here, why the capacitor in parallel means the capacitor always extracts AC. For AC it is offering low reactance path. That's why it should be parallel. Whenever it is parallel, it is going to extract AC, and it does not allows DC. That's why that allows DC through the load resistance RL. This is the reason. Okay, whenever in case of inductor, what happened here? So in case of inductor, here it should be followed by, this is the inductor. So let us suppose here this is both AC and DC. It is flowing through the inductor we have to take. Then what happened? So what is the formula for inductance, inductive reactance? XL is equivalent to, so omega L. Omega L means 2 pi FL. So for DC what happened, Nana? So for DC there is no frequency. DC no frequency, right? So that's why no frequency means what happened? XL becomes 0. If XL becomes 0 means what it is the meaning? There is no reactance, there is no opposing force for DC. If there is no opposing force for DC, then it allows, that means DC allowed by the inductor from input terminal to output terminal. So that's why DC is flowing. Understanding? But what about AC? So in case of AC, what happened here? So let us suppose here this is the AC and XL is equal to 2 pi FL. So for AC frequency component is there, and also inductance is large value we are taking. As the frequency value is more, as the inductance value is large you are taking, then what happens? XC also large. So whenever XC is large, then large opposing force. Large opposing force for what? Large opposing force for AC. So that's why what happened? It does not allows. It does not allows. For example, if it is the ideal, then XC is equal to infinite. If it is the ideal, for ideal inductor, XC is equal to infinite. That means infinite opposing force it is there when the AC flowing through the inductor. Hence the inductor does not allows the flowing of the AC component. So that's why the inductor should be in series to the load resistance RL and the bridge circuit. So pulsating DC, like that here we are using. So this is pulsating DC here. This is pulsating DC. This pulsating DC, if you are giving here, pulsating DC means what Nana here? AC plus DC is there. Okay, so that AC will not allowed through the inductor. Only it allows DC, and that it does not allows AC. Hence what happened? Only DC is flowing through the load resistance RL. In this manner AC was rectified. That's why the inductor should be series. That's why the name, what it is so called? The series inductor filter. So that is the name here we call like that. Series inductor filter. What is the definition? We have to see. So a high value of inductor should take, there also high value of capacitor you are taking, here also a high value of inductor or choke, that is inductor also called as choke, whatever the word or terminology you may use, both are same, right Nana? is connected in series, definitely in series here, but there parallel here in series. Remember here, in series with a rectifier element. So rectifier and the load. So in between the rectifier and load, you have to connect an inductor of large value of inductance in series, as shown in the figure, is called as what it is? The series inductor filter. Understanding? So what is the principal phenomena behind the working of this one? Right? So when the output current, I output of the rectifier increases. So in the graph here I have to explain this one. So whenever the output current increases above certain value means average current it is there, nana. Okay, why? Because current it is always in the pulsating DC increases, decreases, increases, decreases, increases, decreases. In the pulsating already we observe. See here, this is pulsating, increases, decreases, increases, decreases, increases, decreases. So that's why what we are taking, there is an average current here you are taking. This is average current. This is the average current. Okay, so that level here it is maintaining above certain value means average current. This is average current. So if the energy stored in it in the form of magnetic field, what happened here? So if the rectifier output current increases above certain value of I average, then what happened? That extra current is stored as energy in the form of magnetic field within the inductor. Right? So what the formula here, inductor? E is equal to half Li naught square, otherwise half Lim square, whatever the formula you may use here. Im means maximum current, L means inductance. In previous classes, energy stored in the inductor you already learned. So that extra current is stored as a electromagnetic field in the form of E is equal to half Li square, and this energy is given up. This stored energy is there now, half Li naught square. That energy is given up when the output current becomes below the average value. If above the average value, it stores. If below the average value, it can giving. So in this manner what happen? It is always maintaining a sustained current at its output. That means stable output current at its output. So even if pulsating DC increases, that means 0 to maximum, maximum to 0, 0 to maximum, maximum to 0. Here we are watching here 0 to maximum, maximum to 0, 0 to maximum, maximum to 0 we watched. But here in this one what happened? If it is exceeding the I average here to here, then it stores as a electromagnetic energy. For example, if the pulsating DC current, output current decreases than the average value of current, then it gives what the stored energy is there, na? That stored energy it is going to release. So that is the principal phenomena behind the working of this, the series inductor filter. Now already we know that the impedance circuit. So for example, when we are considering, this is the impedance circuit here. So this is the load resistance. What happened here? This is the output, and here we are applying, this one is the input terminals. Right? So this is RL. Then what happened? The impedance Z is equivalent to, here the impedance itself, that means inductor itself it has some resistance. Why? Because through the length of the copper coil it is having some resistance according to its length. Okay, so approximately 0, nana, that is for ideal R is equal to 0. So for normal cases R may be 0.1, 0.1, like that. Here it is there here. So it is having resistance, and also it is having some impedance. Impedance means what? The resistive component and the reactive component. So the combination of resistive component and inductive, reactive component is called as the impedance. So impedance of the circuit Z is equal to formula, what is it? Square root of R square plus XL square, where R means what, nana? The resistance of the inductor, approximately 0 ra. No need to take here actually. So XL means formula omega L, that is 2 pi fl here, xl value. Now substitute. Z is equal to square root of r square plus 2 pi fl whole square. Then how much we got? So for r, z is equal to square root of r square plus 2 pi fl whole square. So here this is the impedance. Understanding? So now first we apply DC. What we come to know? For DC, f is 0, no frequency. For DC current, no frequency nana. So that's why what happened? Frequency you apply 0 here in this place. So R already 0 and F also 0 means Z is equal to R is equal to 0. Why? Because the resistance of the inducting coil or choke becomes 0. So due to that reason, there is no impedance. There is no impedance means what nana? Here Z is equal to 0 means, so there is no opposing force for DC. Hence DC flows through the inductor. DC flows through the inductor very happily, like that here. Right? So the next, so second point, when we are following that for AC. So if you are taking that AC, just you see here. Then what happen if you are applying the AC means the next point. Now coming to that here. So for AC, what happened for AC? The frequency is very large. Frequency is very large and also the inductance value also very large. Hence what happened? Z is equal to R square plus XL square. Otherwise Z is equal to R square plus 2 pi FL whole square. Here in this one, F value, L value increases means definitely Z value also increases. So hence what happened here? Z is equal to, for example, R value 0 you have taken, then Z is equal to what we are taking here? So that XL square. As XL is very very large, then impedance also very very large. That's why what happened? The choke offers high impedance. For what? To the AC component. For DC component Z equal to 0. We got that here. So for this is ZDC or DC is equal to 0. But for ZAC, what happened? ZAC is equal to XL square. We got. So for AC, it is offering that a large impedance means the AC does not flows high reactance force offered. Reactance means opposing force offered by the inductor. That's why it does not allows. If it is the ideal inductor, then the AC flowing through the inductor becomes 0. For ideal case, we are writing AC is equal to 0. So this is about principal phenomena behind the working of inductor. Okay, listen students. Now we have to discuss about the working. Okay, so in that working, just you have to listen. What about here? When the rectified current starts from 0 to towards the maximum. So see here. So in this one, whenever the output current, that means the pulsating current. See here, this one is. So this is the output current. This one is output current. So whenever this output current starts from 0 to, and here this one is the maximum, I maximum. So maximum value. Okay. So whenever current is here, the current is increasing from 0 to maximum. Then what happened here? So when the rectifier current, see here, when the rectifier current starts from 0 towards maximum, the inductor opposes the rise of current. The inductor opposes the rise of current by storing up energy in its magnetic field. So see here, when the current rises from 0 to maximum, then what happened? So this rising up here, this rising up opposed by the inductor. So opposed by the inductor means inverse direction. If it is increasing, here it is in the negatively, it is going to increasing. It is increasing from 0 to positive and it is increasing from 0 to negative. Likewise here we have to take until it reaches the average current. See here, this is the average current point. Until it reaches, it is going to increasing. Okay. So whenever the current exceeds the average, okay, whenever the current exceeds the average, then what happens? Here it is going to change the direction from 0 to positive. So that's what happened. It is also changing the direction negative to 0, like that here, in this manner. Okay, now at this point what happened here? Now the waveform, it is decreasing from 0 to 0, that means 0 to average, so 0 to certain value. So whenever it is going to decrease, that decrease also it is opposing. It is decreasing from 0 to negative. That's why it is decreasing means it should be increase from 0 to positive. It is 0 to negative decreases means it increases from 0 to positive likewise. Right? And again from here you see, so after certain a value, this is called I average, this orange line, average, I average. So whenever it exceeds the average, what happened? The stored energy it releases. Now this much of energy it is there, on highest energy. That energy now ready to release. So here to here it is going to release. Right. So here to here it is going to release. Why? Because the output waveform becomes decreases. That's why during that time it is going to decrease its stored energy in the form of magnetic energy. Stored energy in the form of a magnetic energy. How much it is? Half Li naught square. Right? So again this, what happened? The pulsating DC rises. Again here it is going to rising from 0 to maximum positively. 0 to positive it is increasing. That's why it is also rising from 0 to negative. See here, it is rising from 0 to negative until a value here, until a certain value. So whenever it exceeds the certain value, so then what happened here? Obviously automatically here it is going to get increases, like that here as shown in the diagram. Now again what happened here? Here to here, when we are watching, here the current becomes decreases from positive to 0, positive to 0. That's why here it is decreasing, that's why it is going to increasing to 0 to positive. So in this manner here, if here it is giving this kind of wave representation. So likewise here. So approximately continuous waveform here it is giving. It does not gives the 0. So this is called as the output waveform. So continuous, this is always continuous. So it does not become 0. Even if the pulsating DC is 0, but the output across the inductor does not going to get 0. So that is the working phenomena. So again you see that when the rectified current starts from 0 towards maximum, the inductor opposes the rise of current by storing up energy in its magnetic field. Right? So due to that reason what happened? So the voltage across the load is less during this period. So here see that. So whenever it is soaring, this is less voltage here in this one. This is VL. VL or current, output voltage or output current here, whatever you may take here. Right? Next second point. So when the rectified current starts to decreasing, that means here to here start to decreasing, I maximum to 0. Then what happened? The inductor opposes this fall. This fall, the inductor it opposes. This is the inductor output. This is the inductor output. This one is the output of pulsating DC, that is rectifier output. Okay. So the inductor opposes this fall and supplies the energy to the load. So why? Because here whenever it decreases, this decreases opposed by the inductor, hence the stored energy it releases. That's why 0 to maximum here it is going to increase. See here, increases. It decreases means it is increasing. It increasing means it is decreasing. So every time both are opposing to each other. Thus the current through the load and load resistor RL never drops to 0. Right? So and the circuit yields almost the continuous current in the load. Continuously it is giving the current at the load, right? So this is about the working of the series inductor filter. So this one is the circuit diagram. So this one is the rectifier. In the rectifier output there is a pulsating DC. In the pulsating DC, a choke, the large value of choke is, so large value this is, okay, the large value of choke, it will be connected in series in between the rectifier element and load resistance RL, is called as series inductor filter. Okay, so how much of DC current it is flowing here in this one, IDC. So that IDC or VDC is given by, already derived in the previous classes. IDC is equal to Im by pi and VDC is equal to 2Vm by pi, where Im, Pm, Vm are the maximum values of voltage and current. Understanding? So this is about the series inductor filter. So this waveforms here you have to draw likewise here. Whenever it is going to increasing, it is going to increasing in the negative sense. If it is increasing positive sense, it is going to increasing in the negative sense, right? For example, if it is going to decreasing, then it is going to increasing. In this manner, here you have to draw the diagram, right? So for first 2 half cycles, what the wave repeat, the same here it is going to repeat for the remaining half cycles. Okay, Nana? Now we have to discuss about advantages, right? So what are the advantages of the inductor, series inductor filter? Okay, now you see here the series inductor filter advantages. So the first one is, so here sudden changes in current is smoothen out. That means here it is giving always the continuous waveform. So how we have to write here? That sudden changes, the sudden changes in current is smoothen out. Smoothen out means sudden changes in current means this is suddenly increasing, suddenly decreasing, suddenly increasing, suddenly decreasing. But here the output, what happened here? It is smooth output here it was there in the filtered output. So it is suddenly changing, but here there is no sudden. So gradually it is going to increasing and gradually it is going to decreasing, and here in this manner it is not become zero. It is forming the continuous stabilized output, right? So sudden changes in current is smoothen out. So the next advantage, improved filtering action. Here with comparison of the capacitor, here there is improved filtering action is there. Filtering action at high loads. Okay. So high load current across the inductor L. So this one is the second advantage, right? So next one is the disadvantages. So what the disadvantage here? The first one is the reduced output due to drop across load resistance only. So that reduced output, okay, that is due to drop across the inductor. So actually you see here, this one is the original current, original pulsating current, I maximum, this much of current it is there here. So but this much of current it is dropped from maximum value to average value. From here to maximum value to the output current decreases from maximum to some average current value. It was decreased due to why? The reason is due to the inductor. So the reduced output voltage or current due to drop across the inductor L, right? And the second one is bulky and large in size. This one is bulky and large in size. So third one is not suitable for half wave rectifier. Third one is depends on load resistance RL. So here it is also the filtering action depends on the load resistance RL, right? So as the load resistance decreases, then there is a ripples across the output. Hence it is that means these are the disadvantages with this one, right? So now that a series inductor filter has completed. In the previous class that parallel capacitor filter has completed. So in the next classes we have to discuss about that L section and pi section filter. L section filter also called as input inductor filter, and pi section also called as the capacitor input filter, like that here, right? So thank you very much.